In Orgo 2, you will need to understand the relationship between linear and cyclic form structures of sugars. In case it motivates you to study this concept more, this is also stressed on the MCAT. Firstly, here are the stars of the show, the linear and cyclic forms of glucose, the latter of which is commonly represented either with a Hayworth projection or chair conformation. Though they look completely different, these two forms are actually the same molecule. They are freely interconverted in solution due to the interactions between water and its many polar groups. Let's start with the linear structure of glucose and try to form the ring structure from it. First, you must remember that the linear structure drawn here is a Fischer projection. In other words, this is not actually a straight line. The backbone of carbons is actually bending inwards into the page as suggested by a Fischer projection. This is how it looks, with that in mind. Notice how cyclical the linear form appears when you draw its stereochemistry. Now, let's perform the interconversion reaction. Remember that we are viewing this reaction in the context of being in solution, so the hydroxyl group on carbon 5 can be ionized by water, making it highly nucleophilic and able to attack carbon 1. Additionally, this means there are also protons available to neutralize the negatively charged oxygen that results from this reaction. Here is the cyclic structure that results, represented both as a Hayworth projection and a chair conformation. But since carbon 1 was sp2 in the linear form, two cyclic products can result. Each of these products are referred to as anomers. You can either draw each anomer or represent them both with a squiggly line in place of the carbon-to-oxygen bond that differs in stereochemistry between them. Carbon 1, which was attacked by the hydroxyl group on carbon 5, is called an anomeric carbon. You can easily identify anomeric carbons on sugars because they are bound to two oxygens. To differentiate between these anomers, we identify them based on the stereochemistry of the anomeric hydroxyl group and call them alpha and beta anomers. The difference is really simple. The anomeric hydroxyl group of an alpha anomer points downwards on a Hayworth projection, while that on a beta anomer points upwards. Here is everything we have discussed thus far, summarized. Notice that the linear straight-chain glucose structure makes up only less than 1% of the glucose in solution. You can also see the anomers represented here as chair structures. And notice that the beta anomer is more present in solution than the alpha anomer. This is due to the 1,3-diaxial strain that occurs in the alpha anomer. It is worth noting that the carbon 5 hydroxyl is, of course, not the only hydroxyl group that can act as a nucleophile to form the ring-closing reaction. Theoretically, hydroxyl groups on carbons 2, 3, 4, and 6 could also attack carbon 1. However, these would form 3, 4, 5, and 7-membered rings, respectively, which are less stable than a 6-member ring due to ring strain. Thus, the carbon 5 hydroxyl is preferred. Being that 5-membered rings are relatively stable though, you still will find the cyclic sugar resulting from carbon 4 attacking carbon 1 in solution. Note that anomers exist for the 5-membered ring as well. Thanks for watching. I hope this video was helpful.